Can you turn on the microphone just to test to see?
Great. Hello, can you hear me? If I face this way, you can hear me.
Absolutely.
If I face this way, can you hear me?
Yes.
Great. Cool. That's all I needed.
There'll be a sign-in sheet later.
All right, awesome. Can everyone on Zoom hear okay? We're all
Yes,
good?
thank you.
Awesome, great, glad to hear it. I will just get started then. My name's Bradford Roarr. I'm a research software engineer with the CCV. And recently I've been looking into a lot of digital emissions, carbon stuff, specifically as it relates to software. And today I'm going to be presenting you like one small segment of the things that I've been working on. Cool. So the agenda for today, we're going to do a really super rapid tour of software sustainability as like a concept. We'll talk about the software carbon intensity standard. We'll talk about impact framework, which is a tool to measure or to create artifacts that show your pipelines for climate stuff, as well as a demo of how we can do this stuff for our own work within our supercomputer. Please stop me and ask questions at any time. I'm much better informally than I am formal, so you'll be doing me a favor if you ask me a question, so just keep that in mind. Cool. So I wanted to start off with what software sustainability is, and as it's defined by a bunch of different folks. This is, sorry about this, let's just do this. Great, cool. Software sustainability is an effort to measure and mitigate the impacts of the way that we build, deploy, and run our software. So software is interesting in that it is not a physical thing, but it does have an effect on the environment that we live in just by running it. So the information communication technology sector is globally, or was globally, around 1.4% of emissions, which is pretty nuts. The current estimates for how much that is around 5%. That number is pretty highly contested. Some people say around 2, some people say around 8. It really depends on who you talk to. So 5 feels like it's nice and in the middle. What's really interesting about this is more than 50% of those emissions come from our end user devices. So those are our laptops, those are our cell phones, those are our desktop computers, our PS5s, like whatever. That stuff accounts for more than 50% of the emissions from the information communication technology sector as a whole, which I think is pretty fascinating. So all of us have a part to play in this, and I think it's really nice to keep that in mind. Like this is something that we can affect by the way that we consume technology and by the way that we use technology.
Brad,
Yes?
does that include like production of end user devices or just
Yeah.
production and use? Okay.
Yeah, it counts as production and use and transportation as well. Yeah, there's this cool new concept that's been coming out of France for a little while called like digital sobriety, which talks about how people should be consuming less devices. So instead of getting a new cell phone, trying to make your old one work for as long as possible, or trying to install Linux on your desktop so that you don't need a new computer to run Windows 11 or whatever it is. But there's like pushes to reduce your consumption of those artifacts, I guess. Now, that number that we said over here, this 1.4 and this 5%, just for comparison, airlines are around 2%. The whole airline industry is around 2% of global emissions. So information communication tech is above that, which is pretty interesting. But there's a huge difference, right, between airlines and the devices that we consume. We all know that there's a few billionaires who fly way more than the rest of us, so their carbon impact is disproportionate to ours. But in this particular case, we all use our end user devices. There are a ton of people who have never flown, but there are a lot of people who use cell phones and other digital devices. So I think it's interesting to keep that in mind as well. I know that we've been talking about, we collectively as humans have been talking a lot about artificial intelligence and the way that the artificial intelligence boom is going to affect like the need for more power and the need for more data centers. But that is kind of, the need for data centers is there regardless of whether or not there's artificial intelligence or the desire for more data centers. So this is some materials from Goldman Sachs when they were talking about energy predictions for what they are going to be investing in terms of banking, financial stuff. And this is kind of their projection. So you can see that artificial intelligence does matter, and I'm not saying that it doesn't, but also data center power is increasing across the board, with or without artificial intelligence. And the other thing that I found really nice about this particular plot is it talks about how we are not getting any more power center efficiency gains, like data center efficiency gains. They're just kind of plateaued out because we've reached kind of the limit of what we can do in terms of making our data centers more efficient. I mean, maybe that's wrong, but it seemed to be a trend for a little while now. We're also starting to see a lot of gas companies kind of participate in this growth of data centers. So this particular slide is from the growth. It's from Enbridge, who's a liquid gas pipeline company, and they are kind of correlating data center locations with their pipelines. So a lot of new pipelines are being planned in proximity to gas pipelines. In fact, like famously, this is from Business Insider, but famously, there will be natural gas at the Stargate data center if that ever becomes a thing. So that is supposed to be like a 360 megawatt facility built in Texas that will be burning natural gas. So a lot of this expansion in data centers in general, and specifically for artificial intelligence, is powered by gas, not renewables. So I think that that is kind of an interesting thing to think about. The gas industry has even hailed AI as its savior. Like there's an article in Gas Turbine World that talks about how AI is the savior of gas turbines, which is pretty crazy.
Going back to the efficiency slide, I guess how has it plateaued if we haven't got to the renewable energies or?
So these power gains have to do with how efficiently we can run the hardware that's contained within the data centers. So can we make our switches or our servers more efficient? And our power distribution, stuff like that. So it's all the things that run within the data center. It doesn't kind of include the stuff that's outside of it, if that makes sense. Cool. Awesome. Great. So there are like two main ways that we can be measuring the impacts of the software that we're running. We can talk about the impacts of the power that is consumed when we run our software. And we can also try to understand the energy and materials required to build the devices that we use to run those calculations. So I'm going to hit you with a couple of definitions. These are nice to know. Operational emissions are the emissions that result from energy used to run our infrastructure. So that can be the energy that runs servers and data centers. That can also be the energy that's used to charge your cell phones. All of that is considered to be operational emissions. You may also hear operational carbon. They're kind of used interchangeably. I may use them interchangeably. It's kind of sloppy, but that happens. The second definition I wanted to offer is embodied emissions. And these are the emissions generated by harvesting materials, manufacturing, and transporting of goods. So this is the mining of rare earth metals. This is the manufacturing of your processors. This is the, all the stuff that goes into making these aluminum-bodied MacBook Pros or whatever else you happen to have, and shipping them to you. This also includes the shipping. So is anyone here familiar with the GHG protocols, the greenhouse gas protocols? Is that familiar? Kind of? Cool. So you might hear people talk about GHG protocols, specifically like Scope 1, Scope 2, and Scope 3 emissions. Scope 1 emissions winds up being the things that we burn directly. So the gas that we put in our cars, or the fuel that we burn in order to keep our houses hot, that is direct emissions, or Scope 1 emissions. And then Scope 2 is this, the operational emissions. So that comes from the energy that we buy and use for other things. So that's the stuff that's coming off the grid. And then Scope 3 is kind of everybody else's stuff. So Scope 3 includes all of the supply chain that comes from down the line.
Would Scope 3 contain the disposal of devices from there? Where would those emissions fall?
Yeah, absolutely. So the question was, do Scope 3 emissions include end of life for these devices. And yeah, generally that's where it's accounted for in scope 3. Yep. Cool. Any other questions? Awesome. So now I want to get into a specific standard for measuring digital emissions. This one is one of many different standards. This one I particularly like. It's relatively new, and I think it's pretty cool. It's called the Software Carbon Intensity Framework, and it was designed by the Green Software Foundation. And it's actually now an ISO standard, which is really exciting. So this is officially recognized internationally as a standard for measuring digital emissions. It was ratified by ISO in April of last year. So really new, really cool. And we're going to go kind of more into the details of how this thing works. So people abbreviate it SCI, and that's for software carbon intensity. And they have a few design considerations that went into this. They want to make sure that it can be easily understood and quickly understood. They want it to be flexible enough to work for any software systems that you can think to apply it to. SCI is not affected by carbon offsets. That's really important. So if you're buying offsets to your voluntary carbon offsets to say like, we're green, we're offsetting our emissions or whatever, that does not count for SCI. You cannot count that towards lowering your scores. The SCI uses real-world data. It uses observations from how your software runs in order to generate these scores. And now that it's an ISO standard, it's going to be pretty easy to compare this apples to apples across different organizations, which I'm really excited about. So if this standard winds up being adopted by a bunch of different people, we'll have easier ways of comparing the digital emissions of different organizations. Cool. So some common critiques, I just want to point this out before we get too far into this stuff. The common critiques of the software carbon intensity standard is that it compounds supply chain inaccuracy. So that would be a lot of the embodied carbon that we were just talking about. So that embodied carbon, someone's operational carbon is someone else's embodied carbon and vice versa, right? So it winds up being counted multiple times. That is definitely true. So there is double counts for embodied, there's double counts for supply chain stuff. That's totally fine. And it combines weird metrics, right? So the metrics that you have for building your piece of technology would include the materials that go into it, as well as the emissions that are the carbon equivalent emissions that are being emitted by that manufacturing process. Yeah, and so the SCI scores do combine those metrics. My personal rebuttal, I still think the SCI is really cool and useful. SCI is for decision making. It's not necessarily to perfectly accurately describe the emissions of the thing that you're running. It's trying to decide whether or not it's better than it was before, or whether or not it's better than someone else's service, right? So designed for decision making, not for accounting. Those are two kind of different domains. Another thing that I really like about the SCI scores is that it includes the embodied carbon, which means that there's a factor, and we'll go more into the details of this in just a second, but there's a factor in the equation that you use to calculate SCI that incorporates the lifetime of the hardware that you're running it on. So if you keep your hardware for longer, your SCI score goes down, which is huge, because the more we don't buy new devices, the better our carbon costs or our carbon score should be. So I think that makes a lot of sense there, even though it may not make sense as an accounting tool. Does that make sense a little bit? Great. So now I'm going to go into the straight up equation for all of this. So all of this can be found in their specification, but I've kind of boiled down all of the math into a couple of different equations that we're just going to go over pretty quickly to talk about what they are and how they work. So at its core, the SCI score is the carbon emitted per functional unit of time. That functional unit of time can be anything. That can be requests made to an HTTP server. That can be database calls. That can be Oscar jobs. It doesn't really matter what that functional unit of time is. It's just, we just need to set it in order to work with this equation. Sam?
Is carbon here carbon dioxide equivalents?
Yes. CO2 equivalents, yeah. Yep. Okay. So we break this down, and so remember those definitions from before. The SCI score is the operational emissions plus the embodied emissions per functional unit. We can break that down further so that our operational emissions are equal to our energy times our region-specific emissions. So wherever you are in the world, your grid is generating power, and that grid generates power in many different ways. Here in New England, our power mix is mostly natural gas. We have some nuclear, we import some power from Quebec, they have a bunch of hydro, but most of our power comes from natural gas. So depending on the time of day or how much gas we're burning or the time of year, there's going to be some factor that you should add in to determine the emissions of the energy that you're receiving to run the software that you have. You can get all of these emissions data by the EPA and different NGOs. I'm working on getting a contract for Brown to get access to watt times data. They're a really cool startup out of Berkeley who do carbon forecasts, like 72-hour forecasts of what the carbon emissions are going to be like for different grids in the area. I know Electricity Maps does a lot of the stuff in Europe. And then you can find some more coarse data from the EPA. Yeah. Cool. All right. And embodied emissions are kind of fun because we kind of take a slice of the hardware based on how much time we're using it for and how much resources we are using on that device. So here our embodied emissions are equal to the total embodied emissions times the time share that we are using it for times the resource share. And again, we can break that down further. So the time share winds up being the time we preserved it for over the expected lifetime. So in our particular case, when we think about our supercomputer, when we submit a job using Ethibatch or whatever, we request an amount of time for that job to run. So that would be like the wall time for your Slurm job. The expected lifetime is how long we keep those servers. So my understanding is that we keep them for as long as their warranty is, which is around 5 years, and then we refresh the hardware. So that's kind of the lifetime, and then we are using it for a very specific portion of that lifetime. Likewise, when we submit a job to Oscar, we're requesting some resources, and that will be a percentage of the total resources on the system. So then we can kind of figure out what fraction of that we're using and kind of carve out the little slice that we're using for any given job. When you slam it all together, it looks like this. It's kind of like scary and complicated, but really it all boils down to grams of CO2 equivalents per functional unit of time. And that's really what the SCI score is all about. So it's not too crazy. I've presented it now in 5 minutes or something, so it's not bad, but it is, the devil's in the details, right? Like it's hard to measure some of these things. It's hard to understand how to get information on certain, like embodied carbon is particularly hard, but yeah. Cool. So now that we know a little bit about what software carbon intensity is and how to generate those scores, there are a few things that we can do tangibly to reduce our carbon intensity scores. These are defined, again, by the Green Software Foundation. The Green Software Foundation defines 3 different pillars of software sustainability. I've added one because I think it's important. There's energy efficiency, hardware efficiency, carbon awareness, and education. I think like talking about this stuff really matters as well, because there's just like a small number of us who are just doing this behind the scenes. It's not really going to help anything. But if we get this information out and we all participate, it will have a much larger effect. So energy efficiency is kind of what it sounds like. Use less energy. So if you're using more efficient languages like Rust or Go versus JavaScript or Python, that might save you some energy costs. There's some really interesting papers on what programming languages may or may not be more efficient for what use cases you have. And then considering like how and when you run your software. Do you have a batch job that needs to be run all the time? Do you need to rerun these results right now or at all? Can you not do that? I mean, the best way to save carbon is to not do that work, right? Hardware efficiency is all about better using the resources that we have available to us, better using the hardware, extending the lifetime of that hardware. So if you find more efficient algorithms, you can request less RAM or less CPU or whatever, and theoretically that will extend the lifetime of the machines that you're running on. You can also pack more services onto single servers. This is something that's done a ton in industry with things like Kubernetes. It's specifically designed to cram as much into one server as possible. So we're seeing a lot more of this just in general. And what's cool about these two things is they also make sense from like a financial perspective as well, right? So if you use less energy and if you use your hardware better, you're spending less money. So there are those fiscal incentives to do this stuff. That's just kind of part of how this works. The third one is carbon awareness, and I think this is one of the more interesting ones. And this is understanding our local power mixture and then making our software do things differently depending on that local power mix. So an example of this would be, this is my favorite example of this. Recently, Windows Update has changed so they are carbon aware. So they will check, I think they've even partnered with WattTime, but I could be wrong about that. But they will check the carbon forecasts to see your local power grid, what the power generator is going to look like, and then they will schedule their updates for a time where there is either like a bunch of renewable energy or the carbon intensity is particularly low in your region. And that's when machines are updated. I think that's really cool. And so people are doing a lot more of that. That's just one example. Yeah?
I'm curious, that may be what they're attempting to do, but Windows Update also has a really terrible reputation for never working when you wanted to and
Yes.
forcing you out of what you're trying to do,
Mm-hmm.
whether you want the update or not. So I'm curious, has there been any trustworthy reporting on the actual carbon impact of that software change? Do we know that it is in fact improving things, or is it just kind of a mess?
I think that's a really great question. So the question was, is there good reporting on whether or not the Windows Update stuff actually reduces the carbon emissions? And I think the answer is no. I have not seen good reporting yet. I've just seen Windows say like, hey, this is a new thing that we're doing. I'll be curious to see the white papers they put out. I'll be curious to see the third-party analyses, but it's relatively new, so they haven't finished whatever pilots they're doing or whatever. So we'll see. Yeah, but I think it's just an easy one to point my finger at. But there are definitely other examples of this. People are starting to shift workloads, like when they run workloads in time, so that they run at night or they run, when there's a bunch of wind or solar. People are starting to shift jobs regionally. So if there is a region, so instead of running things kind of in the middle of the country where there might be more natural gas or coal plants, you can shift where your job runs to somewhere that may have solar right now. And that's called region shifting. So people are starting to like do this stuff more often. It's more like buried in, there aren't really great examples for me to point to and like concrete examples, but this is something that industry is doing for like batch jobs and stuff like that. Does that make sense? Cool. And then the last thing, like I mentioned, I think we can start to talk about this stuff and try to measure it ourselves. The Green Software Foundation has a really cool training. You can become a green software practitioner. I did, it's not that bad. If you hit that QR code, it will take you to a Linux Academy class or a Linux Foundation class, and then you can run through that and it'll give you all the basics. It'll go much beyond the stuff that I'm talking about today and show you other things that you can be doing in order to reduce the impact of the software systems you work with. Cool. All right. So the next thing I want to talk about is the impact framework. So the impact framework is a software system for calculating these sustainability numbers. It doesn't need to be, it doesn't need to calculate sustainability numbers, but that's what it's primarily used for, and that's what it was designed for. So the whole crux of the impact framework's methodology is these manifest files. Inside of these, we're going to go through this much more in depth, so don't worry if you can't read that, because I've got plenty more examples. Manifest files are all written in YAML. They're designed to be immutable. They co-locate your data your observations about how your software is running, as well as your pipelines for computing these sustainability numbers all in one single file, so that you should be able to rerun them no matter what. So it kind of keeps them all in one little bundle. They are designed so that you can have like really complicated nested structures for interesting systems. If you are looking at, I don't know, like what it takes for someone to purchase something on Amazon, you might be going through many different systems in order to get there. The Impact Framework manifest files are flexible enough to reflect a database server, a web server, some cache stuff, and to be able to aggregate all of those numbers together, which I think is really cool. So I was going to do some demos, kind of show you more about these manifest files, talk about them more specifically. I also have some code that will allow you to make observations about some of your software that has been running in the supercomputer. There are some caveats. One, it only looks at CPU right now. This is a work in progress. I'm still trying to make it work better. It relies on the same systems as JobStats does, if you've heard of that. We only save that data for the past 30 days, and we only collect that data if the thing's been running for longer than a minute. So those are kind of the requirements. If you've had a job that you've run on Oscar that has taken longer than a minute to run, and you've done that within the last 30 days, this is something that you can follow along with. Cool. Awesome. So, yeah, cool. So this is the repository. If anyone wants to follow along, feel free to hit GitHub up and look at this stuff. We're going to look at it together in just a second. And we can even run through some of these manifest files, see what they look like, and do that. Cool. So let me know when you all are ready to move on, and then I'll just pull up the repository and we can talk through it. Everyone good? Can I move on? Brad. All right. So I'll just start by, we can just start by looking at, that's totally the wrong one. This is the one. Great. All right. We can start by just looking at the repository. So in this repository, we've got a couple of things. We've got these 4 YAML files. These are all different manifests. They all do slightly different things. We're going to wind up walking through combining your operational emissions with your embodied emissions to generate your SCI score. And we can do that by looking at a bunch of different YAML files. This is a Node project, so Impact Framework was written in TypeScript. So you do need Node to follow along. And then there's also Job Carbon here. Job Carbon is a Python script that I've been using to generate YAML that will fit into the Impact Framework structure that contains observations about the jobs that you've run on the supercomputer. If that makes sense. Cool. In this resources directory, I have a couple of different things. I saved the eGrid data from the EPA, which contains regional emissions data. This is the most recent one. I saved it out of paranoia for obvious reasons. And then I have this CPU model file. I've kind of gone through and made a CSV file of all of the different nodes that we have in the supercomputer and what processors they have, so that we can use that in order to calculate some of the embodied emission stuff. So it's kind of a tour of the repository. Does anyone have any questions there? We all feeling okay? Cool. The README is long, so hopefully it answers all of your questions. If it doesn't, let me know, and I would be happy to fix it. Were you all able to access this okay? Did I make this public? Cool, great. Awesome. Now let's run it. So I have, bear with me, my screen is not mirrored, so this is going to be challenging for me. Great. So this is a manifest file. We talked briefly about manifest files before. Is the font big enough? Can everyone read this? Is this cool? Great. This is a manifest file. It can be broken into two different sections. It kind of has head matter, and then it has the observations of your system. So up at the top here, it has some metadata about your system. So here, it's got a name, it has a description. Those are kind of self-explanatory. Tags, if you have many of these, you can tag them as like cloud or CPU jobs or whatever. It doesn't really matter, but that is just for your own internal accounting. And then the important part is that it has a series of plugins. So Impact Framework works by running your observations through a series of plugins in order to generate some numbers. So in this particular case, we have a plugin called coefficient, and it multiplies an input parameter by a coefficient, and then it outputs that back into your observations. So it kind of continues to grow those observations with a bunch of different stuff, and then you have the option of aggregating those results at the end. The second block down here is where our observations live. This tree structure is really interesting. This is where I said you can get arbitrarily complex, so you can have web servers and database servers and separate them out differently. In our particular case, in this extremely simple case, we just have one child. We're kind of doing the same thing in the more complex examples. We're not doing anything too wild, but I think this would be an interesting use case for like Oscar array jobs, for example. You may have one job that runs a bunch of other array jobs, and then you could collate those into one single observation. You have defaults. Defaults provide some parameters that don't change throughout the entirety of the observations that you have. So the amount of RAM that you request is not really going to change for the lifetime of the job that you've run. So you can use that as a default there. Then we have a pipeline. The pipeline defines how we're going to run things. Observe and regroup are interesting. They allow you to shuffle your data. So if you do have those complex use cases like array jobs or microservice architectures or whatever, you can regroup the observations using that. And observe allows you to run scripts to pull things in dynamically. But for today, we're just copying and pasting our observations directly into our manifest files. And so this is the manifest files that I've generated. This one I built by hand. It's really boring. It doesn't do much. The other ones I generated from kind of a test job that I ran on Oscar. And we'll be seeing those in just a second. So if we want to run these, this is probably too small. Cool. If we want to run these, the command, well, the first thing that you'll need to do in this repository is an npm install. Always do an npm install. That will install the dependencies for whatever it is that you're working with. Without doing that, you just won't have the software to run. But once you have that, the command to run things is npx ifrun-m, and then you pass it the manifest file. And so in our particular case, we're going to run through the basic demo YAML manifest file. If I hit enter here, we can see our output. So our output kind of shows you your inputs. It tries to make sure that like everything matches up appropriately. So in our case, this is just the exact same stuff that we saw before. It adds an execution block with an environment so that you know what commands were run and on what machines in order to make sure that the stuff is reproducible. And then it also contains the output, and the output's going to be down here. So we had in our pipeline, we had the CPU utilization and CPU utilization doubled. So now if we go down here to our outputs, we can see now that we have our CPU utilization and our CPU utilization doubled. It's not super interesting, but this is how it works. And then we can expand on the number of plugins that we use and how we combine those plugins to actually do something interesting. Feeling okay so far? Cool, great. All right. So let's look at the second one. The second one is I'm going to cheat. I'm going to go to the third one. Let's look at the third one next because I think it's a little more simple than the second one. I just did it in operational and embodied because that was the way the spec was written, but doesn't really matter. Okay, so this one has the same structure, right? So we have this name, tag, description. It also has aggregation. So this is defining how we are going to, what we're going to aggregate at the end of our pipeline. So we have a series of observations. We're going to calculate the embodied carbon for each one of those observations, and then we're going to add them all up at the end to get a final number. We have a list of plugins as well. There's a lot more plugins this time because we're doing something different, which I think is really fun. The first thing that we're doing is we're looking in that CSV file. So that was the CPU model thing. We're going to essentially query on node name. So we're going to try to match our observations node name, and then we're going to pull in everything from that row in the CSV file into our observation so that we can do some more calculations with it. Then, as I mentioned before, the impact framework is specifically designed to be calculating these software carbon intensity scores. So they have plugins to do a lot of this work for you. We are leveraging the SCI embodied plugin in order to be able to calculate the embodied carbon for this particular CPU job. There's a lot of parameters that I didn't set. All of this stuff is really rough. It's very superficial. There are definitely better ways to create a software carbon intensity score, but for illustration purposes, I thought we could just go through something simple and not get it too crazy complex. So right here, this is a very silly thing that they did, but lifespan is defined in seconds, which I think is fun. So this is 5 years in seconds. It's not a decision that I would make, but that is the decision that they made. What's up?
Question for the lifespan. How is the lifespan generated? Is it like a company makes a device, they maybe buy this thing, they want to buy a new device after 2 years, or is it like some ISO?
Totally. So the question was, how is the lifespan generated? That is generally a policy based on the organization that you work for. So in our particular case, in Oscar, we have servers that are installed in our server room. They have a warranty. Once the warranty is up, we try to get them out and replace them with something that does have a warranty so that we can get them repaired. And that's the way that Brown deals with this sort of thing. If we had a policy in place to keep them for another 2 years after their warranty expired or something, it's just policy. So it really depends on the place that you work and how you want to handle these things. Cool. All right. So as I mentioned, we are leveraging this embodied plugin. So we're just pulling straight from that embodied plugin, and it is going to generate that embodied score. You can also provide metadata for your outputs. This is something new that we haven't seen before, which gives you, it allows you to describe the outputs of your pipeline with their units and specify how they should be aggregated. So that's kind of why that exists there. So in this particular case, the output parameter that we're generating is carbon embodied, which you can see right here. We're giving it a description, we're giving it a unit, and we're saying that it should be aggregated over time and components. Cool. Down here, this is going to look similar but different. I generated this from a job that I ran, I don't know, like a week ago, maybe more. So this comes straight from Oscar. This is the Oscar job ID. I have defaults. Defaults are based on the SBatch script that I use to run my software system. In this particular case, I allocated two cores and 4 gigs of memory. And then in this pipeline, it's getting a little more complicated, right? So in this particular pipeline, we're doing the CPU lookup. So we're looking into that CSV file. We're pulling all the information that matches our node name, and then we're calculating the embodied carbon based on the data that's coming from that CSV file. And now you see here that this looks a little different in terms of the inputs. Now this is what the job carbon script does. So if you choose to install that in your Oscar home directories or wherever, if you run it, this is the observations that it will generate for you, and it can be copy and pasted into a manifest file like this. I hope to expand upon that and make it more user-friendly in the future, but for now, it's in this repository. You can copy it if you want it. But this will go through and it will look at, we have a metrics database called Prometheus that stores different statistics about how your software is being run, and it stores them every 30 seconds. So these observations are being run every minute. So this is in minutes. And we can see here what the system use was. So this is how much the CPU utilization that the system used, the number of CPU seconds that were allocated total, and then the number of CPU seconds that were spent on user processes. If that makes sense. The node name, again, is coming from the information that is found within that metrics database. So it's being pulled straight out of that metrics database and it's automatically populated there. And then everything is required to have a timestamp. And that's an epoch timestamp based on when this thing was run in the past. Cool. Any questions? Feel okay? Great. So we can run this one in the same way that we ran the other one. And it gives us different results. So if we scroll up, we can see our outputs are, so this winds up being all the inputs. So the inputs are, this is the inputs where everything is pulled in from the CSV file. So the node names are generated by the job carbon script, the CPU model full, CPU model, thermal design power. This is all stuff that is in that CSV file that kind of explains different aspects of our CPU jobs. And then all of this stuff goes into calculating the embodied carbon. And in this particular case, if we look at it aggregated over time, we spend on this particular Oscar job 0.1 grams of CO2 is the embodied carbon for our particular run of software on Oscar. Make some sense? Pretty small number. Again, this is just like a little test program. I really want to run this on things that are more representative of a real workload. I just haven't gotten there yet. So soon, I hope. Operational carbon, this is the one that I said that we were going to skip because it gets a lot more complicated. This gets a lot more complicated. So the way that we're doing things is we're calculating the CPU utilization that is based on the total number of CPU seconds that were allocated in a given input slice. And we are, we're calculating that utilization based on the user seconds and the total seconds. And then we are kind of using that to scale the thermal design power of the CPU. This is admittedly not a very good way to generate the operational carbon numbers for CPU stuff. A much more robust way would be to leverage some of the statistics that are contained within spec power database. It's this really cool company that just runs benchmarks on servers. And so you can see like power benchmarks for different CPUs. You can use that to kind of better infer what power your system is using, how much of that power goes to your memory or your main board or whatever else versus your CPU. So that would be a much better way of doing the thing that I'm doing here. But right now we're just taking a fraction of the thermal design power of the CPU. The thermal design power for a chip is how much power it is designed to dissipate. And so rack manufacturers, like people who run data centers, care about this number because they want to make sure that things are designed to dissipate the amount of heat that we expect from a given CPU or GPU or something like this. It is interesting to note that CPUs have much better numbers than GPUs. So with CPUs, you can actually see like the spec power benchmarks for how much power this thing is using for any given number of operations that it's doing. Really cool data set. With GPUs, we don't have anything like that. And they choose not to publish those numbers because it is not in their interest to do so. So we don't really have anything but the thermal design power. So we wind up doing this kind of analysis for a GPU because that's the best we got right now. Hopefully we can build some better metrics than that. Okay, I'm going to scroll down first, and then we can scroll back up in a second. So this is the pipeline that we're using here. So we're calculating the utilization. We're doing a lookup on our CSV file. This is going to be doing the same thing that the embodied carbon did, looking at that CSV file, pulling in all the information from that node. We're going to convert our usage to wattage. So that utilization, we're going to multiply by the amount of watts that's being used per core on any given machine. Everything needs to be in kilowatt hours. So we're converting our duration into hours. So every one of our observations happens each minute. We just want to make sure that that's in terms of hours. Then we're converting watts to kilowatts. We're calculating the energy, and then we're calculating the operational carbon. And that's kind of, so this is a much more complex pipeline. As you can see, it uses a lot more plugins. And if we scroll up, we can like look at some of these different plugins that we're using. So this one's very exciting. We're dividing two numbers, right? So we're dividing the total CPU seconds by the user seconds to get the utilization. We're doing a CSV lookup. This is the same as embodied, no big deal. Here we're multiplying. So it winds up being like, a lot of these steps are really simple, but we have to be very explicit in the way that we configure things for reproducibility. Like these are meant to be immutable artifacts that can be shared, and you know exactly what observations that this is running on, and you know exactly what calculations were made. So it's tedious, but I think that that is important in some ways. But a lot of this can be automatically generated. That is something that I hope to do in the future. It's not something I've gotten to do yet. Similarly here, like we're converting minutes to hours, like kind of boring. Impact Framework does have a way for you to do complex arithmetic expressions inside of strings, which is kind of neat. So I didn't need to do that division explicitly. I could do something else, right? Which is kind of nice. It's just convenient. Yeah, so that's kind of how all of this is working. And then, yep. And then, like we were doing before, we're defining some of these outputs. Here we're giving a description of what the operational carbon is, what the units are, and then how we aggregate that stuff. The observations, the inputs here, all the observations about the systems, are the same as they are in the embodied one. So it's using the same data that we were using to calculate the embodied carbon. This particular time, it's being used to calculate the operational carbon. So if we run this one, we can see our operational carbon is a little bit higher. That is 0.65 grams of CO2 equivalents per kilowatt hour for this particular job. Cool. Any questions? Yeah.
I kind of a dumb question.
I love it.
I feel like a lot of this is super like low level, just helpful. But,
Yes.
like, can I use this on my jobs? Like, can I set this up to like
Yeah.
run on every CPC job that I run?
Soon. So I know exactly what you're saying, and I think it's a really important question.
Yes. I don't know what the process is, but
Yeah, I'm working on making it better, but right now I have a little bit of something. So I'm kind of jumping away from the DSCI right now. We're going to do something a little different just for a second, because Jocelyn asked. So Jocelyn was asking, how can I use this stuff? I have some scripts. So there is a job carbon script that is contained within the repository we were just looking at. That can be installed on Oscar to run on certain jobs. So I have jobs right? This is a random job that I ran. It just runs some dumb benchmark. It runs it for 5 minutes, whatever. And I can take this thing and I can run job carbon. I can just paste it as input.
Like, can I just stick this like run job carbon.py at the end of all my smart scripts?
Sure. You'll have to do a little bit of work after that in order to like get it into the right format, which is annoying, and that's something that I'm working on. But if we run this, this is what generates the inputs that go into these manifest files. So if you want to do the rough CPU evaluation that we're doing here today, you can copy and paste your numbers into the existing manifest files, and it will work. And you will get a very, very crude estimate of the software carbon intensity for your given Oscar job. This it's totally, it's something, right? It's better than nothing. But it specifically works on CPU jobs only, and I'm working to change that. This doesn't include memory yet. This doesn't include GPU yet, but those are all things that we can be adding to this. Yeah, so you can do this to generate, you see the format, right? Same format. So it's got that tree, children, job number. That's how you would generate your inputs. Same deal. Yep, and I tried to make it easy, so you can literally copy the line from this thing and use that as your input. Note here, we care about this one. We don't care about these two because we want the overall job. We don't want the batch and the extension or whatever that is. Those are different steps of the same job. So every job gets a couple of different steps. We only care about the one where you're actually doing your work. Does that answer your question?
Yes.
Awesome. Cool. Yeah, no problem. Yeah. So we were looking at those inputs, right? Those inputs would go right here. That's like everything that was just generated would go right here. You would still need to provide your defaults and your pipeline. Those would still need to go into that same manifest file, but you can cram your observations right here and it would work great. Yep, and you can do that right now and it'd be great. Everyone should do it. It's gonna be really exciting. Cool. So that's operational carbon. Any questions there? The last one I got is throwing it all together to actually generate an SCI score. Cool. So this is the last one. This one actually incorporates both the operational carbon and the embodied carbon in order to generate that SCI score. If we go all the way down here like we were doing before, sorry for the scrolling, everyone, we can see our pipeline. So this is just the same. I just copied and pasted the pipeline from the operational one and the embodied one, and I stuffed them into this. And then I added one extra step at the end to calculate the SCI score. So that's kind of what's going on here. In this particular one, it requires some defaults. This grid carbon intensity, that is coming from EPA data that is based on the average emissions for Rhode Island coming from our power generation in the year 2023. Cores allocated comes straight from your SBatch script. Memory, same deal. And jobs, this is a funny parameter. You just need it there in order for the SCI plugin to work. I'm not entirely sure why they did it like that, but that's the way it works. Yeah, Tim.
Where it says cores allocated is 2, and then all the time points down below, like it's going to 2 different nodes.
Mm-hmm.
I was going to get confused between cores and nodes. So, like if I were to...
I allocated one node. I allocated 2 nodes, each with 1 core.
Okay.
Yeah. Mm-hmm. Yeah, but I was trying to make sure that this would work for jobs that use multiple nodes, because I think that that's important, because that happens all the time. Yeah, but yeah, there are going to be bugs in this, and I really want to fix all of them. But like this is, so I may have made an error somewhere about mixing up cores and nodes, but I think that's what I did. Yeah, cool. Awesome. So the big things at the end is that we're summing carbon. So we sum the operational and embodied numbers. We just add them together, and then we pass it to this SCI thing, and that creates our output. And those are kind of the last two steps of this thing. So it takes that embodied, that operational, adds them together, and then passes it to the SCI plugin to calculate that final number. And if we run it, 04, we can see our aggregated stuff. So our SCI scores are pretty low for this particular job. So the SCI score is, technically it has units. Technically the units are grams of CO2 per kilowatt hour. But really they encourage you to count it as a score for the reasons that we were talking about before, because it double counts carbon in a bunch of different ways. So this is designed to be like unitless. So you can consider your SCI score to be unitless. So our score is 0.048. That is a number. Now, if I run that again with a different job, I can compare those two jobs and I can see which one is higher or lower. And that's really what the software carbon intensity score is designed for, is figuring that difference out. If that makes sense. Cool. And that is kind of everything I had. So yeah, if anyone has anything else, let me know. I'd be happy to answer any other questions. If you have thoughts or suggestions, I would love to incorporate them into this work. I think it's really fun, and I'm excited to do it on real stuff soon. Cool. Thanks, everyone. This was great. Sure, I can. How do I make it available?
There's going to be a recording available on the DSI YouTube channel, but also.
We'll try to
what's
put.
What's your name?
I'm Alyssa Silver.
Alright. So that's Brad.
Sounds great, yeah. And yeah, give me an email or anything if you need help with anything. I'm really excited about this stuff. And thanks everyone on Zoom. I appreciate your time. Bye, y'all.